Okay, just a video on what we've been doing so far in advanced functions, grade 12. So B1, this learning goal that we're on right now, is all about understanding radians as a way to measure angles, and we're going to connect it, or we're just going to recap it with our special triangles from last year. Okay, so in your previous years doing math, you've been using degrees. So you've kind of been saying like, you know, going around in a full circle would create a 360-degree angle. So if you're referring to stuff like that, we said like this is 0 degrees, this is 90 degrees, this is 180 degrees, 270 degrees, and then back to 360. So previously we would have used degrees to represent this, but now we're switching over to radians. So we want to use radians every time we talk about angles now. Okay, so now we did the whole bike-rim experiment, and we pretty much learned that, we learned that 1 radian, actually, if you were to take a circle and determine its radius, actually, I'm just going to show this in a different color. So we determine its radius. Then we take that same radius length and we fold it along the arc. So that's also the same length. And this right here is the same length. Then the angle formed in there is equal to 1 radian. So that's how radians work. Okay, so then we also talked about, like, for our bike rim, the circumference of our entire circle is 2 times pi times radius. The circumference is equal to 2 times pi times radius. If we were to break our circle up into, like, radius, like measure each radius around the circle, it means like we're dividing the circumference by our radiuses. So if we were to place like how many radiuses can we fit around our circle, those r's would cancel out, and it turns out we can place 2 pi radiuses around our circle. So that's pretty much like saying in one entire revolution of a circle, there are 2 pi radians. Or another way to think about that is 2 pi radians are equal to 360 degrees. Or another way to say that is pi radians are equal to 180 degrees. So if we were to draw our circle on this axis, we know starting here it would be 0 degrees. Going up to this point here would be 90 degrees, or what am I doing? Writing this all in degrees. 0 radians. Going up to this point would be pi over 2 radians. Going over all the way along, we would normally say as 180 degrees, but now we would say as pi radians. Down here would be 3 pi over 2 radians, and then back to the beginning would be written as 2 pi radians. So we're now just switching over and using radians instead of degrees. And we can use this conversion of, if we wanted to determine what 1 radian was equal to, we know 1 radian is equal to 180 degrees over pi. So we can use this conversion to kind of help convert between radians and degrees. Okay, so let's say we wanted to convert 45 degrees into, we want to know how many radians that is. Okay, so we take the number 45 and we can set it, we can multiply it by our conversion factor. So our conversion is 180 over pi, or pi over 180. So in this case, we're going to do pi divided by 180, because we want the degrees to cancel out, and we want there to just be radians. So this would equal 5 times pi divided by 180. And instead of leaving it like that, we would always reduce our fraction to lowest terms. So we just look at the 45 and the 180 and see if it's divisible by anything. And in this case, you can divide the top and bottom by 45. So the top will just become pi, and the bottom will become 4, because we know 4 times 45 would be 180. So 45 degrees in radians, pi over 4 radians. And that's how you would write it exactly. If you wanted to write it as a decimal value, you could also just divide pi by 4, so 3.14 divided by 4, and figure out what that equals. I don't have a calculator, so I'm not going to do it. Okay, let's say we wanted to convert like a trickier number, like 67 degrees into radians. So we times it by pi over 180, and the degrees cancel out, so we get 67 pi over 180. But then we see that like 67 and 180, we're not going to divide it by anything to reduce it to lowest terms. So in that case, we would just go ahead and calculate it as a decimal value. So we would say 67 times pi divided by 180 will equal 1.17 radians. So like sometimes it's nice to leave it in exact form, like this pi over 4 looks good. But in this case, that's a ridiculous number. So in this case, maybe it would be better to put it at a decimal value. Okay, let's convert the other way. So let's say we wanted to convert like 2 pi over 3 into degrees. So in this case, you can just multiply it by 180 degrees over pi. So our pi's will cancel out, and this will be equal to 2 times 180 divided, or 2 times 180 degrees divided by 3, which will equal 180 divided by 3 will be 60, and then 60 times 2 will be 120. So it'll equal 120 degrees. And whenever you convert to degrees, always round to the nearest degrees if there's any decimal places. Okay, awesome. Let's talk special triangles. So way back in grade 11, you learned about special triangles. So I'm just going to go through the derivation of it. So you have an equilateral triangle here. And when you have an equilateral triangle, each angle is 60 degrees. I'm going to write that as a radian though, so I would say each angle is pi over 3 radians for an equilateral triangle. And then if I were to take my equilateral triangle and split it down the middle here, 2 right angle triangles, and that angle was pi over 3 at the top there, but if I have to split pi over 3 in half, then each side becomes pi over 6 and pi over 6. So then this whole thing would be equal to pi over 3. Okay, so then if I said my equilateral triangle, if I said each of my side lengths in my equilateral triangle was 2, then this side right here and this side would each be equal to 1, since it's a split right down the middle. So if I just take half of that triangle and I just draw out the 90 degrees side, like one side, then what I've got is a pi over 3 angle and a pi over 6 angle, hypotenuse of 2. Down here is 1, and to figure out that third side, I can just use a version of the Pythagorean Theorem, like c squared minus a squared equals b squared. So 2 squared minus 1 squared, so 4 minus 1 is 3, and then to figure out what the side is, I'd have to square root it. which is the square root of 3. So this guy right here is our first special triangle. So you want to remember this in whatever way you can. I personally know how we derive it, so like I got that down. So then I can easily get my special triangle just by remembering that. But if you need a trick, something like remembering the pi over 3 angle across from the root 3, like develop some of those ways to kind of remember your special triangle, because you want to be able to set it up. So even if I drew your special triangle like this way and I wrote pi over 3 here and pi over 6, you still need to figure out which side is which. So I know my hypotenuse is 2. I know right across from pi over 3 is root 3. This side would be 1. So you need to be able to draw the special triangle in any rotation. Okay, let's talk about the second special triangle. So let's start with a square. And in a square, each of those angles is 90 degrees or pi over 2 radians. So each of these is pi over 2. And each of our side lengths is the same. Let's say they're all equal to 1. So then if I split my square down the middle, like down the diagonal like this, that would make these angles here split in half. So instead of pi over 2, those two angles would now be pi over 4. Same with this side would be pi over 4. And this side's pi over 4. So if I just talk about my 190 degree triangle there. So I've got a pi over 4 side, a pi over 4 side. I know that each of my side lengths are 1. And if I had to find the length of my hypotenuse, I could just do c squared equals a squared plus b squared. So 1 squared plus 1 squared is 2, and then I would have to square root it. So this guy right here is your second special triangle. So you want to remember this triangle too. Okay, so now that we've got our two special triangles, I'm just going to draw them here so we have them to refer to. So we have this guy, and then our other special triangle looks like this. So these are our two special triangles. So they're really great for giving us exact values of trig ratios. So if we wanted to find, for example, what's the sine of pi over 4? I'm curious. Okay, so we pick our angle, pi over 4, and then we just use our knowledge of our trig ratios, sine, cos, and tan. So sine is equal to opposite over hypotenuse. So my opposite side is this side, and my hypotenuse is always across from the right angle. Sine of pi over 4, like opposite over hypotenuse. So that would be what sine pi over 4 equals. And that gives us an exact value. There's no rounding there. We don't get some crazy decimal. We get the exact answer, which is what we want. I don't like decimal places. And then there's one other thing to remember, and that is we don't like radicals in the denominator. So to get rid of that radical, we actually need to multiply the top and the bottom by root 2, which is called rationalizing the denominator. So what happens is the numerator will become 1 times root 2, and the denominator will become root 2 times root 2, which is root 4. And we can simplify that to root 2 over 2, because the square root of 4 is just 2. So as it turns out, sine of pi over 4 is actually equal to root 2 over 2 in its better notation. Okay, let's find another one. Okay, so let's say we wanted to find out what is the cosine of pi over 3. Okay, so we want to find the cosine of pi over 3. So we find our angle, cos pi over 3, and then we look at the adjacent and hypotenuse. So for cos, our adjacent side is the one right beside the angle, so the 1, and our hypotenuse is right across from the right angle, so 2. So the cos of pi over 3 is just 1 over 2. Okay, we wanted to find the sine. All right, let's do tan. We haven't done that yet. let's say we wanted to find the tan of pi over 6. So now we pick our angle, pi over 6. The opposite side would be 1. And the adjacent side, since tan's opposite over adjacent, would be root 3. And we know we can't leave the root 3 on the bottom, so I would multiply the top and bottom by root 3. And I would get root 3 over root 9, which is just equal to root 3 over 3. Final answer. Okay, so that's how you use special triangles to figure out exact values. And we all know from last year that the sine and cosine curves repeat themselves. So they look like this. And it continues on in both. So just to relate yours back to degrees, so this is 0 degrees. This guy right here is 90, or pi over 2 radians. This guy right here is 180, or pi. This here is 270, or 3 pi over 2. And this right here is 2 pi. So you can kind of think about this in terms of quadrants. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. So this is kind of like quadrant 1, 2, 3, and 4 on our graph. So we know that our values kind of repeat themselves all the time. So far using pi over 6, pi over 3, and pi over 4, we've only been using quadrant 1. So like pi over 6, pi over 4, and pi over 3 are all these values right here. So if you notice, they're going to repeat their values again over here in quadrant 2. And then in quadrant 3, they're going to repeat themselves, but they'll be negative. And then they're going to repeat themselves again. So using this knowledge, we can actually extend our special triangles to go to the other 4 quadrants in a graph. So for angles greater than 90 degrees. So let's say I wanted to find out what is the sine of 2 pi over 3. Let's say I wanted to find that out. So I'm trying to figure out an exact value without punching it in on my calculator. So I would go to my grid, 0, pi over 2, pi, and 3 pi over 2. My initial arm is always on the positive x-axis. And then to create this angle of 2 pi over 3, I would have to figure out how far my initial arm is going to rotate. So it's actually going to end up to be in 2 here. And to think about that, if you're not really sure, look at the angle 2 pi over 3. It's less than pi, because it's like 2/3 of pi, really. So I know it can't be as far as pi. And it's bigger than pi over 2, because pi over 2 is like a half pi. 2/3 pi is bigger than a half pi. So you just kind of have to look at, using your knowledge of fractions, where would that belong? So this angle 2 pi over 3 is right there. And for us to calculate our special triangle, we're going to create a triangle by attaching our terminal arm to the x-axis, which will create a 90-degree angle. And now we have to figure out what's our related angle right there. So our related angle would end up being pi over 3. And to figure that out, I would take pi. So that's like the complete all the way along. And then I would subtract this angle here, 2 pi over 3, to figure out the part that I have left there. Sorry, I'm just going to get rid of that. So I would take pi, and then I would subtract my 2 pi over 3 to figure out what my related angle is. So I'll just make them have the same denominator. 3 pi minus 2 pi is pi, and q over 3. So I know my related angle is pi over 3. So then now I know this angle up here is pi over 6, and I just have to add in the side lengths of my special triangle. So pi over 3, okay, so this is root 3. And this hypotenuse is a 2. And this bottom part here is going to be a -1 since it's on the negative part of the x. So there's our special triangle. To find sine of 2 pi over 3, we use this related angle to answer that question. So we use opposite over hypotenuse. So opposite is √3, and hypotenuse is 2. So sine of 2 pi over 3 is equal to √3 over 2. Also, there's this thing called the CAST rule that we learned last year, CAST, and the CAST rule just tells us which trig ratios are positive. So in quadrant 2, it turns out the sine ratio is positive and all of the other ones will be negative, which makes sense because let's check out what would cos of 2 pi over 3 be. Cos of 2 pi over 3 would be adjacent, so -1/2. And the tan of 2 pi over 3 would be opposite over adjacent. So the opposite's √3, and the adjacent's -1. So that would just equal -√3. So you can see those two are negative, and the sine ratio is positive. Okay, let's try one more. This video is super long. Okay, let's try to find the primary trig ratios of an angle like okay, let's see if we can do the 3 trig ratios of 5 pi over 4. So we'll try to find sine, cos, and tan of 5 pi over 4 without using our calculators. So we're going to use special triangles for them. Okay, so first we have to figure out what quadrant they'll be in. So here's 0 radians, here's pi over 2, here's pi, here's 3 pi over 2, and we're back to 2 pi. So this is my initial arm here. And then 5 pi over 4 would end up being, it's going to be bigger than pi because 5 over 4 is like 1.25. And it's going to be less than 3 pi over 2. So it's going to be in quadrant 3 here. So this angle right here is 5 pi over 4. So if we want to create a triangle like this, then we have to figure out what is our related angle right there. So if I'm going to do that, I think I'll do 5 pi over 4 and subtract pi from that, which will leave my related angle. So I'll just make that 4 pi over 4 so it has a common base. And 5 minus 4 would just be pi over 4. So this value right here is pi over 4, means this is pi over 4 as well. So if we want to write our side lengths down now, we've got our pi over 4 special triangle. So this length will be -1, this one would also be -1, and our hypotenuse would be, √2 actually. Okay, so if we had to fill out these trig ratios, we're going to use our related angle. Sine is opposite over hypotenuse, so -1 over √2. And if I rationalize the denominator, that's -√2 over 2. Cos pi over 4 is adjacent over hypotenuse, so -1 over √2. It's actually the same, which makes it -√2 over 2 once we rationalize. And then tan of 5 pi over 4, tan is opposite over adjacent, so that becomes -1 over -1, which equals 1. And using our CAST rule, let's just make sure that makes sense. So this quadrant tan is the only positive guy, and that's true. Tan's positive and the other two are negative. So that's how you do special triangles. Okay, one more thing we talked about. This is a lot, but anyways, the one more thing we talked about was the unit circle, and using that to help us do stuff. So the unit circle is just like what we've been doing, but it places a circle on the axes, on the xy axis, and it says that this circle has of length 1. Ugh, I can't draw a circle. Okay, so we said the radius here has a length of 1. So if we wanted to say the coordinates of all these points on our unit circle, we would say this point right here would be 1, 0. On the x-axis, the y-axis, this point right here would be 0, 1. This point down here would be negative 1, 0. And this point down here would be 0, negative 1. So that's our unit circle. And then we can create our terminal arm and initial arm like we were doing before. So our initial is always on the x-axis here. And then our terminal arm goes out to the circle like that. And it has a radius of 1. And then if we wanted to turn that into a triangle, we would connect it to the x-axis. So. And then we said if we wanted to label the sides of this triangle, we would call this side x, we would call the vertical side y, and we would call the hypotenuse r, which is just equal to 1, a unit circle. And then we said we could write this, and the angle is here. So then we said we could just write our trig ratios, sine, cos, and tan, using those variables. So sine would be equal to opposite over hypotenuse, so y over. And since r is just 1, then sine theta would just be equal to y. And cos is adjacent over hypotenuse, so that's x over r. And since this is a unit circle, then cos theta would just be equal to x. And tan would be equal to opposite over adjacent, so that's y over x. Which we can't really do too much with that. We could just leave it like that. Or we could also kind of extend it and say, since y is sine theta, we could say that tan is equal to sine theta over cos theta, since it's equal to x. So this guy right here is actually one of our trig identities that we're going to be using in the future. So yeah, the unit circle kind of helps us prove trig identities, and also the unit circle can help us figure out angles that are right on the x and y axes. So remember, this is 0 radians, up here is pi over 2, this is pi, and this is 3 pi over 2. So let's say I wanted you to find out what the sine of pi is equal to. So it's really hard, there's the terminal arm. It's really hard to make a triangle when it's on the axes, or when it's on the x-axis. We can use this knowledge. Sine is equal to y in the unit circle. So sine of pi would just be equal to the y value, which is 0. So we know sine of pi is 0. If we wanted to find the cosine of pi, well, cos is always just equal to x, so the x coordinate is negative 1. So the unit circle can kind of help us find all those values that are right on x or y axis. Okay, hope this video helped. This is pretty much, well, most things in B1.